Hello, everyone, and welcome to Handmade Hero, Show We Code a Complete Game live on stream. We are, well, honestly, don't really know what we are at the moment. We have our lighting actually working, and I think mostly what we need to do now is tune the lighting to make sure that we're getting reasonable results for what we want. And then after that, we just have to optimize it. Now, we could also just optimize it now. And the reason that I say that is because looking at the actual profile in terms of what is slow right now, and this is doing an entire lighting solution. As you can see, actually this entire room is lit by the actual lights. It's not, there's no cheating here. So this is actually spreading throughout the environment and so on. We can actually probably do optimization early if we wanted to. And the reason for that is just that if we look at what our actual timings sort of announce, as far as I can tell, although we are spending some significant portion of the time that we probably would want to optimize in stuff that's specific to the current lighting scheme. Actually, the majority of the time is still in the raycast, so we could just optimize our raycaster, and that would probably give us a large speed increase if we get a little more serious about that. And it doesn't really matter, it doesn't have much to do with the actual lighting itself. So changes we made to the lighting wouldn't really be a big deal at that point. Now, one of the things that I'm not sure about too in terms of lighting is we also never really looked at the sort of decay time of the lighting. And I think at the moment it's something like 20 frames. Ish. I mean, it's hard to say exactly what the frame is because it kind of blends out over time, which is not really a particularly specific way of thinking about it. But, right now we're doing 95/5 blend. So I think, you could sort of say that over 20 frames, you've got a fair bit of the new lighting in there. And that could certainly get reduced. So, that could go down to something like 2. And still not be horribly laggy. If we wanted to take a look at that, like I said, I'm not really sure how we want to look at that, but the update voxel call that we have there is, where that happens. And you can see that here we lerp using this tupdate blend function. And so whatever we set the solution's tupdate blend to, that's really what's going to be determining that rate. So we can set the tupdate blend to whatever we want. And so in here, oh, wow. So this was actually even more. So it's really a trade-off between response speed. Like this is extremely fast response for an indirect lighting solution, right? Which is normally updated pretty slowly. And so if we want to, that can drop down dramatically. So here's like a really, much, much deeper. And so you can see if we reduce the blend dramatically, you can see how slow it is to update, right? Like you see how slow the highlight fades from here to here. But as a result, you get like no noise, right? And so you can control the difference between the response rate and the noise pretty easily just with this parameter. And what this parameter should be, we don't know, right? Like, I have no idea what it should be. You can see that it's pretty usable, probably, at this rate, maybe. And so it's still not too bad in terms of light lag, but you still get a little bit of flicker in there, right? You can see a little bit of that flicker as these change. And to be honest, I'm not really sure also about that flicker. I don't know if there's other things we're doing that may lead to more of that than is necessary as well. Like we haven't really taken a good look at it. But you can sort of see that somewhere there's a smooth point for our current scheme, and it's somewhere around the 1/60th, it looks like. Because I can still see a little bit of flicker here, right? So, in terms of that, I don't know what we want to do there. I'm not sure what the correct trade-off is for that. And casting more rays would also do it, but we don't really probably have the budget for it. But either way, it seems pretty reasonable. So at the moment anyway, I'm not sure we really have to worry about it too much because it seems pretty good. And furthermore, like right now, we're not really we don't do anything particularly fancy in our actual sampling to try and reduce the amount of noise either. Like, I don't know very much about sampling theory. I don't spend a lot of time with it. And so it's entirely possible that that could be improved dramatically as well. So I think we're in okay shape there. So then when we look at the other sorts of things that I think, I'm not sure about at the moment, I think, some of the biggest stuff is just, what is going on there? Where is all this light coming from? That seems like kind of a bug, doesn't it? Like, how are these all super bright? So that's got to be a bug. That looks like some kind of propagation of like a bad value. Like, how did this all get bright down here? Let me see if I can make that happen again. I wonder if we have some fill-in bugs and stuff like that. I'm going to go hop over there. So I feel like really that, again, just taking stock of it, I think really what we want to do here is just go and pick one, either, optimize the raycaster, which maybe is a better idea because then it's faster and we can make better judgments about it. Oh, I bet I know what happened. I bet it was the voxel movement. Yeah. You can see it, like, look at that. See how that's propagating weirdly? So something's going on weird down here. Like the light, I mean, is there even any light in this room? I don't know oh, there is a light in this room. All right. So something about in here, like the lighting is just super bright. Probably because it has a ceiling. So it can like reinforce the bounces. The bounces don't escape, right? Yeah. So anyway, I don't know which one we want to do. Let's go ahead and say, like, let's just do this weekend maybe a performance survey, just so we have an idea of how hard it would be for us to optimize further from where we are. And then maybe next weekend, and based on that, we can decide whether next weekend we want to try and do optimization work or whether we want to do some quality work first. And we can see. So again, I'm not really sure about the current performance state of things, and also I'm not really sure about the when we're doing the raycasting exactly how we've been centering this box, right? So if you take a look at this, you can see the lighting domain that we are currently enclosing, and you can see that lighting domain is pretty wide, right? And we may not really want it to be quite so wide. Like, we may want to shrink this voxel so that the actual span of it vertically is considerably less. And that might be a good optimization just right off the bat, because it doesn't really make much sense that we would be doing this, right? It's just not a particularly sane thing to be doing, because we don't need to be simulating this much levels of light in our game. 1 or 2 levels up or down should be plenty, and 1 or 2 levels, when you got up to here, you're simulating like the 3rd or 4th level. I guess I don't know quite how deep these are. Let's take a look. I'm gonna just stack 2 levels on top of each other here so I can see. We should probably have a teleport function in this game. You would think. All right. So here we have, let me see here. Just going to zoom out a little. Yeah, so you can see, like, if that's the stacking rate, we really probably only want 3%. So this is probably twice as large as it needs to be. So I don't really know, like, one of the things we should get working in debug pretty well, because I think it would actually make sense to ensure that we're doing it properly, is to just take the light lookup voxel dimensions and split this out so that we are actually able to do a more squat, like a voxel that's not as tall as it is wide and, or it's not as much in Z as it is in X and Y. You know what I mean? So if I wanted to do this, first I would like to see where this is actually getting used. So I'm going to go ahead and get rid of those 2 and find everywhere that we're still using them. Because there's not a lot of places that we actually are. And so I want to actually just kind of start to clean that up. So here in the light lookup voxel dim for the lighting solution, I think that might be a good place to start getting rid of this, right? So we've got the hot dim getting used here, and really we don't want to use the hot dim anywhere here. If I recall, the atlas themselves should actually have the information about the voxel dim in them. So you can see here that whichever one we're actually working on, we should be able to loop just over that voxel. So the spec atlas is really the one that we're looping over here because that's the one that we're updating. Molly the cat is currently digging in a pile of papers. What are you doing, Bean? You looking out there? You having fun? What are you doing? She really enjoys a cardboard box full of papers. So the spec atlas here will give us the information that we need. So the voxel dim Y there and the voxel dim X here should give us what we need. And you can see here that we've got the Z, and that's going in these slices. I think that's actually fine. I don't know if there's anything in particular that we did here that was weird. And I guess, so if you look at the way we were doing this, it looks like we kind of assumed that we wanted to eventually do it in the other direction round. So you can see we were passing voxel X here, but yet we had the Z on the outside. So I don't actually know if there's any real reason we can't just fix that. So at the moment, I'm going to go ahead and say let's do that. So instead of this being a Z, let's just make that change as well. So what that would be is in here, we would say like, okay, the X is going to be the voxel X, and then here, this will be a Z and a Y. And again, I don't think there's any reason we can't do this, but we'll find out, right? So if that's our iterators, so now we have the Z and the Y here, and then we've got the X here, that also allows us to balance our work a lot more, because before, if we were doing Z slices, we would I think we would definitely run into situations where casting would be occurring out in the middle of nowhere for no reason. And we're already doing that a lot anyway, but at least here, this would minimize that quite a bit by shrinking the voxel down. And once we do that, we don't want to assign sheets because the sheets will be unbalanced, right? Like if we start to detect that we're in an area where there's nothing, we could just not do casts there. And when we do that, we would end up with entire, like, a thread that, like, literally had no work to do because it was in a slice that, you know, didn't actually have any actual geometry in it or something, right? So that's kind of a separate issue, but for the moment, like now, if we look here, this should rearrange this nicely. And then if we go to the work voxel X stuff so that we look at where that's actually being set, we can just make sure that that's correct. And so in here where we assign the work count, you can see all this stuff happening like this with the work count. We want to make that be the spec atlases. So right here we want the spec atlases voxel dim Z would be the work count, and we would basically assign out for each slice of the voxel Z, we would assign that to a different thread, right? Now, I don't know, we may need to assign, oh, sorry, X, not Z. So for each X, you know, each like column on the screen, basically, we're going to be sending that to a different thread. And again, that's important because if we're starting to shrink that Z dimension too, we don't want to only be able to slice on our lowest dimension, right? And we know our X will always be our widest dimension because the screen is wider than it is tall and so on. So once we get in here, that should be all we really need to do. Unfortunately, I don't think the spec atlas actually gets pulled out here, so I should make sure that we actually do pull it out here. Let me just go ahead and pull out both because they're kind of things you want, generally speaking. So I'm going to go ahead and do that. All right, so as we start to push forward on that, let me get rid of any places refer to that here. Okay, so here we look at the spec atlas stuff, and we see the signed unsigned mismatch. That should be fine to just change these to signed. That's fine. Not really an issue. Let's see what else we got here. We don't care about that. So here where we create the number of works that we're going to do here, this memory arena needs to push on however many we think we're going to have for like the X. So I would maybe what I would suggest is this should probably turned into like a max kind of thing. So here I would say this should be like a max like light lookup voxel dim. So like, look, we know we'll never allow more than a 64 or something or whatever. I mean, whatever we can set to whatever we want. And that's for people who want to create sort of static known buffers. So they don't have to allocate them dynamically or do anything else weird like that. Although I suppose in this case, there's really no reason not to. Like, you could just use the frame arena for this, so I'm going to put to do here. Because we could use a temporary arena or the per frame arena. Like, we have sources of memory we could just use for this and that just get flushed at the end of the frame. We don't even have to clean them up. We don't have to think about it. So it would be trivial for us to do that. So this is probably not really necessary, and maybe we should just get rid of it. It's fine for now, but I'm going to put a to-do in there because it's like, I don't really know if we should bother with that. And then we wouldn't have to define this, and it would just make the code, simpler, right? It doesn't have this other dependency. All right, so anyway, but that's fine. So moving through here, those are ones we don't care about at the moment. That's one we want to fix. Here we've got, I think it's just Spec Atlas and Diffuse Atlas, right? Yeah. So let me just go ahead and shorten those names. And there we go. So now I think we're down to just the iterator. And then the part here where the Z-bias program sends down what the voxel dim actually is going to be. And I think for that, that should be pretty straightforward because it's just a compile time. And this one here is where it will actually be specified. So the only one we really have left to deal with outside of the OpenGL layer is this one. And what you can see here is really this one is just used to compute the inverse hot dim, which let's just check out where those are being used. So inverse hot dim here, I guess, is not even used. Is that correct? That's correct. So it's really only the hot dim. And that's only used for the entropy index. So I guess we don't really super care about this even a little bit. That feature is that's just not really used. So the entropy index here, I suppose, So I suppose we can just maybe do, I mean, I don't really know how we want to do this, but it seems like the most straightforward way would just be to sum it up and not actually use the hot dim here at all. So we would just say like, and I could just do this too. I could say voxel dim equals spec atlas. And that way we know what we're dealing with here. Delete this. And then the z, y, and x, those would just be voxel dim z, voxel dim y. And to compute the entropy, we would just say, well, I guess it would be like, plus x, y times voxel dim x, z times voxel dim x times voxel dim y. So just basically computing like a stable value there, I guess. I'm not really sure. And also the sample point entropy part here, I don't know. I'll be honest, since that comes off of the work, I don't know why. We should just make this be something that probably, I don't even know if we want to do it this way. This could just be something that gets incremented, really. I mean, can't it be? Like, where's that even happening? The entropy index itself could just do this. Where we just increment it each time. We could think about that a little bit later, but at the moment, I don't even know that we need to bother with any of that stuff. So we'll have to look at how we want to get our entropy source there, but for now, that's probably fine. All right, so taking a look at the rest of this stuff, where we've got because I mean, really, this might want to add something else, I guess is what I'm saying. Like, we might want to do something like, that, right? I mean, I don't know, but we may want to stride through the thing in a weird way because the other things are going to be incrementing directly. So we may want this to like wrap in some weird way. I don't know, right? We'll probably want to do something saner there eventually, but it doesn't need to be based on the voxel in any particular way. So we're down to just this part of the code now where we're going to do the compile zbias program. And in order to compile the zbias program, we do need to know what the voxel dimensions are. And furthermore, we need to update this piece of code to actually be correct and think about what the voxel addressing is now. Because I believe this was like the last piece of code we had that was still, we didn't ever write it to use a full three-dimensional voxel dimension set. So if you look at what happens inside it, you can see that it's got like just voxel dim times voxel dim in various places, I think. Well, no, it doesn't. Take that back. It looks like actually it's pretty sane. So we should actually be able to just, I think we should be able to just fix these by using whichever ones, So, I mean, there's a couple of places, like here, for example, excuse me, that we're going to have to fix it, but it's actually not that bad. Interesting. So I think if light lookup voxel dim just got a little more savvy and we actually made light lookup voxel dim be a v3, that's really all we need to do here. So if we take a look at that, so light lookup voxel dim here is actually not going to be a %u. It's going to be like a v3 with a %u, and a %u, right? And furthermore, it might actually be %f in this case. I don't know. I mean, I guess it's not going to be a %f because it's never going to be that value. But this right here is probably not a v3s. It's probably a v3 because it's only ever really going to be used for the for multiplying things out by. I don't think it's ever really used for any kind of indexing where we have to have those be integers. I could be wrong about that, but we'll see in a second. So I'm going to pass the voxel dim in here, and then I'm just going to literally write it out. So voxel dim x, voxel dim y, voxel dim z. So now the light lookup voxel dim is actually a 3 wide value. And so wherever we have voxel dim in here in the future, we can muck with it, right? All right, so yeah, we probably want to clean up this shader at some point because there's so much old cruft in here, but we'll do that when we actually do the quality. I'm not going to do that for now. So in here you can see us, well, wait a minute. Am I looking at the right thing here? Why is that? Oh, because that's the exterior. Okay, that's fine. So when we look in here, basically, this is being computed based on the dimensions. And so you can kind of see like the y value that we're looking up is the inverse of the voxel dim, but this is actually now just going to be the z. And when we look at this one, we're now going to have to use the x and the y, right? Because those were the sizes we were computing there were for an xy sheet and just the z count, right? So that's really all we should have to do there. For the rest of them, we just have to look at who's actually being operating here. It looks like, again, here, we're really using the same values over and over. So I feel like we should be able to just pre-compute these. So it feels to me like we should be able to say, look, we've got the like XY sheet, and then we've got the Z sheet sizes, or maybe like XY stride and Z stride, something like that. And these values, once we compute them, we use them in a lot of places. So we just need the Vox Z stride value here, and the Vox XY stride value here. And that's really it, I think, right? So this is the light lookup Vox dim squared. That's the Vox XY stride, I want to say. Again, because you're going sort of across the voxel. And then this one is the Vox Z stride here, because again, you're going down the voxel. Same is true here, I think. So this is Vox XY stride. And this is Vox Z stride. And that's really all it gets used for in here. We then have one more in here where we're saying the light lookup voxel dim Y plus the X times the exterior dim. So producing the center, it looks like, well, I'm not sure. To produce the X coordinate, it's multiplying. Oh, so this is just the X span of the voxel, right? Because for each Y, it has to go 1 in X. So this is just the light lookup voxel dim X dimension. Yeah, because for each Y, it has to go 1 full X, along, right? All right. So light lookup voxel dim, where else is it used? So just here. So to produce the voxel R in this case, this is going to be one where we take the UVW and we, I guess, blow it out to this is the inverse dim, so now we're going to take the forward dim. So that doesn't even have to change because that's going to just be a 3-wide multiply now. So I think that's it, actually. All right, so when we're doing compile Z bias program here, we actually need to use the size of this thing as a voxel, and that's actually something that when we have the settings here, we don't actually know what that is because we don't pass it in here. However, it is actually something that we just kind of know anyway, because the OpenGL structure itself has the spec atlas in it. So we should be able to just say, look, the OpenGL arrow spec atlas here, right? Specular light atlas. Voxel dim is the voxel dim in question. That's what you're going to use for the lighting, so off you go, right? So that's hardly an issue. So finally we get down to this, and now we're just at the point where the setting for the voxel dimensions is picked here. So now we can actually say, we can reintroduce this and say, here's the actual light lookup voxel dim. It's going to be 32, and that's just what it is, right? And now everything should be operating on that, right? And hopefully, if we run it now, we won't get some disaster. We'll just get the same exact thing we saw before, right? And it looks like that's roughly what we get. So now, if we want to change this to being like a X, Y, and a Z, we should be able to start, debugging that now. So if I were to actually make each of these a separate value and use them here to, seed this with something different, I should be able to tweak those values separately, and as I tweak those values, I should get a different shape. So if I look, for example, at that, I should be able to say like, oh, okay, I now want to shrink down the Z, and we should be able to try and figure out where we break, right? So now if I shrink by the Z, and I zoom out here, you can kind of see like that this became more squat, right? But it otherwise is the same. And looking at it, it actually looks okay. I mean, I don't know, like it doesn't look particularly wrong. So it looks like, I mean, maybe we're still doing it properly, but obviously it's pretty hard to say exactly. It does look like our debug drawing code maybe didn't quite handle that as well as it could have, but only the debug code. The actual runtime code looks fine. And one of the things that you'll notice is already, that jumped us up to a much better frame rate as well. So prior to that change, if you look at what we're running at 32 by 32 by 32, if we run it here, you can kind of see the frame rate 125 milliseconds, or, thereabouts, right? Kind of oscillating. We drop that down, and we immediately get, just from reducing the footprint of the lighting thusly, we go down to almost twice as fast, right? And that's sort of what we would expect, because the lighting itself takes a certain amount of time. That amount of time is based entirely on how many places we want to sample the lighting from, plus sort of the constant overhead of producing the diffuse maps, which right now is pretty slow. So if you take out that constant overhead, we doubled the speed of the interior portion. And so as you expect, we get almost twice as fast, right? That's exactly what we would expect to see. And so if I go ahead and hop around now, it's getting much closer to a playable frame rate without us ever actually having optimized anything, just by saying, look, let's not compute the lighting in a bunch of places that we don't actually care about, right? Which seems like a pretty obvious thing to want to do, since obviously you don't really want to compute lighting in places that you don't need it. All right. So I think that's fine, and then we can start to look at some other things here. If you look at the speed too, you can see that we may want to spend a little bit more time thinking about how we're doing these diffuse maps as well. If you take a look at that, excuse me, if we were to take that out of the equation temporarily, so when we're producing those diffuse maps here, if I go over to the lighting code temporarily and I disable the part of the code which actually tries to sum up the diffuse maps properly. So here in the work queue callback, I say, look, just don't worry about that. It's just not, we're not going to do that. No one cares, right? So if I take that out of the equation temporarily and I come back over here, you can see that going away. You can see that again, like we're getting a lot faster just from that. So we would get another, 10 to 20 milliseconds shaved off the time if our diffuse map production code could be done more efficiently. So that's another thing that we would want to potentially think about too, although it's definitely like the shorter end of the stick. But if you take a look at how that's working right now, yes, we did the nominal, we did a nominal amount of work to just like simplify the way that was working by, doing it 4 wide. But what we didn't really do is actually reduce the number of multipliers that are involved here. So if you take a look, this is, if you take a look at our for loops here, this is a 2, right? This is an 8. And then you look at these two, and this is an 8, and that's an 8. Right? So if you take a look at how heavyweight that routine is, it's just a lot of multiplies, right? It's just a lot of multiplies. And we reduced it down from 4096 to 1024 by making it wide, but that's still not great. Like, we would rather this be significantly less than it is. Okay, so let's think about this loop just a little bit, and see if we can't maybe think about ways of making this a little bit more sane. Looking back at the actual runtime itself, and again checking that profile. Go ahead and put this back in. You can kind of see that the profile itself. Oops, sorry. Gotta fix the debug. We gotta clean up our debug code one of these days. It annoys me that it can't do the hot reloading properly. Anyway, so if we take a look here at this part of the code, when we if zero that out, we don't actually get much of anything left in the propagation work. Why? Okay, so what's actually the problem here? It's using like a It's using like a block that's supposedly not supposed to be used for allocating. And I'm not sure. We have to go find out what's going on there. I don't know why that's bad. But anyway, you can kind of see here that compute light propagation work drops down to a fairly meaningless amount of the frame time. So this part, even though the fill light atlas, like these fill light atlas border things, Those are not really optimized at all. They're extremely stupid right now, but even extremely stupid, they just touch so few pixels, I guess, that they're just not contributing to the frame time. So we probably don't have to worry about those, not for a long time. So it's really just this part right here that's our problem for that, for this outer part of the code. And then there's the raycaster. So if we take a look at what's going on here, there's a couple different things that probably could be improved. First of all, just the loads themselves are not great. So the offset from Texel, I don't know how good this is doing. This could probably be done better. We can look at the assembly code for it. But the main thing I want to look at first is just, can I take some of the multiplies out, right? And so what I want to do for that is I want to see how many 0 weights we have. Like if the weights are all 0, I want to know that, right? I want to know that ahead of time. So where we go over to the build diffuse maps thing, which again, this is a good excuse too to make this code, the build diffuse light maps code, better, because right now it's not particularly good either. So right now I want to go ahead and take a look at the performance of this and just figure out, not the performance of it, but what it's actually producing and how that would affect our performance going forward. So what I want to do here is take a look at every time this might be 0. So I basically want to say, 0 W count. And so if we take a look here where this is, where this weights bit is happening. In fact, you know what? I can even just make this a separate thing. So here we are. I'm going to loop over this exactly the way. Oh, you know what? I could even just put it here. So right here. So I'm just going to do this. I'm going to say how many zeros are there. Through each of these, when we get out the W, I'm going to go ahead and say, look, I want to know if all of these are 0. That's not what I was trying to do. I was trying to get that one. If all of these are 0, then we want to know about it. No. Bad cut and paste. And there. So if all of the weights that we were going to encounter in the multiply were all 0, so we basically did not have to sum this one, I want to sum that. I want to count that and know at the end of this how many of those there were. And so I'm just going to set a breakpoint here and have it show me that value, the 0 count value. So like right here, right at fill light atlas border. So I'm going to go ahead and change this to a debug build, which is our slow build. And then I'm going to set a breakpoint on that fill light atlas border. So fill light atlas border, where is the lighting code? There we go. Fill light atlas border. Where are we? Where is that? There it is. I want to stop like there, let's say. And so this way I can just find out like how many of these multiplies are actually useless, because I don't actually know right now, but I would like to know. All right, so basically out of 1024 multiplies, right, we only actually had to do 828 of them because the other ones were 0. So they could have just been skipped, right? So I don't know exactly how we want to do this, but we could try encoding this slightly differently, right? We could try encoding this as basically like a multiply skip list kind of a thing. And I'm not sure. Like, I don't really know exactly how we want to do that. But if you take a look at the savings there, it's that's like saving 10% of the work that you would be doing. And that could be fairly substantial, right? Furthermore, there's a couple other things to consider here. The way this loop is working may be kind of stupid as well. just the way the load is working. So if we were to actually even say, look, we're still going to brute force this because we're just brutish like that. Yeah. So I'm going to look at a couple different things. So first of all, I think the first thing I want to see is let's take a look at what the assembly language code for this actually looks like. Now we know how many zeros we're actually doing here. I can pull that out. And I'm going to go ahead and see what the code looks like here, just to see how bad it is. And then I'm going to see, like, maybe about doing the loads a little differently, just to see if I can streamline it a little bit. Now, if I don't see anything weird, then maybe I won't do that, but we'll see. So I'm going to set a breakpoint here, and then I'm just going to look at the disassembly just to see what it looks like when we actually go through here. So I'm going to make this window a little bit bigger. And here's us, stepping through the disassembly here, right? So if we take a look at where we're actually, I don't know what that's doing. Ignore this window for now. So once we get into the actual... What is happening here? Why is that jumping like that? I think that's just bad, like... No, it isn't. What is happening there? None of that looks particularly good to me. I want to find out what the heck is happening here. So offset from Texel is just supposed to do this. Oh, well, we do have the assert pointer is in bounds. So I may disable that just quickly to... that might be throwing the optimizer a little bit. Hold on a second. So I'm going to do a pound define here. I'm going to go ahead and say that there's a light atlas check pointers thing, and we're going to have that. In fact, you know what I'm going to do? I'm going to have light atlas assert do nothing. And so anywhere that there was assert in here, I'm going to change it to a light atlas assert. Oops. And the reason that I'm doing this is just to make sure that I don't have to pay any price in here when I'm trying to do optimization work. So I can turn on... So basically, I want control over asserts in this particular piece of code, right? Go ahead and stop that. All right. So, yeah, there was way too much jumping around in that code, and I think that that is probably because we still had those asserts in there. I'm not 100% certain about that. But let's take a look. Because this should flow more smoothly here. I would think. What is going on? Oh! Duh. I forgot. I don't have a way to freeze this thread. So we have to turn off multi-threading first. I was like, what's going on there? Yeah. So we still have multi-threading turned on here. I've got to turn that off if I want to step through this really, because otherwise I'm going to be seeing multiple threads stepping through it. So that's, yeah, less good for our analysis. So let's go ahead to begin lighting. It may be that Remedy already has this. I don't know. I've never learned in Remedy if you can step a single thread. Like, step single thread is a great feature to have. Visual Studio, I don't even know if it has it. It's a real pain in the butt in Visual Studio. Remedy may have added a better one. I don't know. But either way, I'm just going to go ahead and say, look, we just won't. Like, that's not going to happen. So multi-threading's turned off. And then we'll run it now. So, yeah. All right, so now running in, I should be able to see this more cleanly. So now if we step through, we should just go straight forward, and we are, I believe. That looks kind of weird. Why does it disappear? It doesn't look like the assembly stepping is working here. George, help. I don't know if there's a newer version, but the assembly stepping doesn't look like it's working. Like I can't actually step per instruction. And it used to work. I don't think we've got X13 pixels with us, do we? Help, George. So I guess I can just look at this code though, even without stepping through it. So if you look at the way this is loading stuff here, it looks like it's doing some aligned loads. Let's see what else we're doing here. It looks actually fairly good, right? Like, did it actually reorder? Interesting. Did it actually reorder the calls? Did it put these two? Wait, it can't have done that. Where are those two calls? Or did it inline them? Hold, please. Yeah, I can't see where this is. So I'm curious where these calls went. Because I don't know if it inlined them or what. Because I wouldn't have thought so, since it has to get called twice. Yeah, so that's weird. So it actually moved those calls up and it jumps back to them or something? I guess. That's just a weird... Did you notice how weird that was? I mean, it may have just done that. I don't know. But it looked like it kind of did something pretty weird there, if this is to be believed, where it changed where those go. Oh, you know what it could just be? It actually looks like just the assembly language here was kind of busted. The stepping was busted. Now it's working properly, right? And now it looks much more sane because we're actually getting to this before we get to the call. So maybe that was just a bad display thing that was happening. Okay. Yeah, because this looks right. Like I was really confused about what I was seeing there. I think that's because it was wrong. So now this looks totally fine, right? You can see it doing a move. It's doing a shuff to that's the broadcast, so that's the load of the spec texel value there, right? So it does a move, and then it gets the value and does the shuff. So here's the mov, and yeah, you can see it's doing the load one at a time. I don't know what the heck that's doing. What? That just doesn't make a whole lot of sense what I'm looking at here either. Well, we'll take it on faith that that wasn't too stupid, but it looks kind of stupid. This just looks like way too many shuffles for what's actually happening. So, yeah, I don't like the looks of this at all. So I would say, actually, let's maybe just clean this routine up first. Because it's easier for us to do that. Yeah. So I'm going to say, look, the way that we're going to do this is we're going to actually load so the spec atlas where we're doing the 8x8 there, let's just say we're going to lock that down for now, and it's got to be 8x8. So we're not going to let this range around. We're going to hand code this. And so it has to actually be sane, right? And so if we did that, we would know that we can load everything. So when we're looking at the spec texel here, right, we know we could load everything for a particular spec texel row with 2 loads, right? Furthermore, if you actually think about how many there are total, so in an 8x8, there's 16 spec texels, right? So actually, you could put the spec texels themselves, if you only cared about that, you could actually put them in registers because there are 16 registers. So you could actually just load all 16 if you wanted to. Now, we can't really necessarily do that because we need some place to store other things, but it means we could do like 4 at a time if we wanted to, certainly. So let's just write at least 1 row here. Let's write that out manually and see what happens. So in here, I'm going to say, look, let's just get where we would be reading this texel from, like this. And then let's load the 2 actual values we want out of there. So I'm going to say, all right, we've got an M128 here. That's the first one, I guess, and this is the second one. I mean, I don't know how we want to actually label these because it's actually the first 4 and then the second 4. So kind of hard to say, but maybe I'll say this is 0 through 3 and this is 4 through 7. I don't know. So when we look at the actual spec texel, we're going to now do like an like load UPS on this thing. And I'm going to load an actual, texel out of this. So here's the M128 for spec texel value. And the same is true here. Only this time, the spec texel value. In the light atlas texel, that's a V3, I guess. I had not considered the fact that this is actually RG and B. So I take that back. So this would actually load, if it's RGB, 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 which it is, right? If it's actually that, then there's more per row. So yeah, so that explains why there were more shuffs in there. Now I get it. I was wondering why all the shuffs were there, but that's why they were there. It's because there's actually RGB. I was thinking I was doing monochrome, but I'm not. All right, so yeah, if we've got RGB, then so that's 3 of the floats times 8. So there's actually 24 float values. So there's actually 6 per row. And this is not the correct way to look at it, right? So if there's 6 per row, it's going to look more like this. And these are offsets by some amount, right? I guess I should probably just duplicate that line. So those are all the values that we actually have. And we then want to like process each one, right? So we want to actually do the multiply here, the multiply accumulate for each of these times the correct weight, right? So we want to do like a load of the weight and then multiply it in. So previously we were, let's just go ahead and move this out here, right? So we need to be able to load these weights, and for each one of, like, the SY is just what it is, and for each one of these we have an SX that we need to load and then do the multiply with, right? So we know that we've got something that looks like this. Right? So we're going to load the weights one at a time. And then we know we have to do this as well, right? So we can actually avoid loading we can actually avoid like specifying it that way by just doing this in the accumulator, right? So the light C itself can be part of that operation. And so all we need to do now is actually get the correct shuffle to produce the weight value we wanted times like a shuffle of these things, right? So, because everything that we want to do for our multiplies is going to come from whatever, you know, one of these 6. So we should be able to do this loop cleaner, right? And make it easier to read and easier to think about how fast it should run by just doing those directly. That's my argument anyway. So if we load everything in, then we just need shuffles here, right? We need to be able to do shuffles. Right? Where we're going to do like something like this. Know what I mean? And those weights, the weights there are the only weird part about it is the weights are actually V3s. So in order to produce the correct V3, we need basically, and it kind of doesn't. I kind of don't know that I really want to do this in V3 anymore. I might just want to do this in actual like X, like written out manually in X, Y, and Z. Or R, G, and B in this case, so they don't have to keep working through it that way. And if we look at the diffuse weight map here, we can also write this in the way that we want as well, right? So I can make this just be the correct series of things to load out in order. So we'll have to think about how that should actually work. So anyway, if we move along here, we know that as we load these in, we have, well, and now that I think about it, it kind of also seems like I could just transpose, so this bit here, I feel like I could just be transposing on the load as well, right? So this kind of feels like it just wants to be done all as one like clean routine here. So let's just keep going with this. So here's my M128 light CR. What's the 0? It's like MM0 PS. There's an MM0 PS. Oh, set 0. That's what they called it. I don't know why they called it that, but they did. And so, you know, I might just even say this is the R, this is the G, and this is the B. And then the transpose there is this shuffle here that we have, again, like, it's just kind of annoying. Like, I just don't know that I want this in this struct. Because once you start to blow it out, it just doesn't, you know, it doesn't really make much sense. So, like, doing that sort of, like, wrapper, you know what I mean? Just doesn't make much sense to me. Having it in the wrapper. So I'd rather get rid of it. So we can still use the shuffle 4x. And in fact, I can still do these as just R type here, which is fine. But I just don't want the v3 version of it. I don't think that's productive. All right. So we can leave it like that, and that's fine. But then what I think I would want to do is this transpose here. I would like the transpose to be done outside, right? And so this part of the code, you know, I would like that to just work that way. Just trying to see if I can still use this type and not be grumpy about it. Yeah, that especially, well, yeah, well. All right, okay. No, you know what? Maybe I'm okay with that. Maybe I'm okay with that. It's literally just 3 of those. I'm okay with that. I can do that. All right. So we can leave it that way. All right. So we can probably leave it that way. I'm okay with that. I overreacted. I was a little bit grumpy about that, but I'm okay with that. That's fine. So if these are all just F3 4X's in here, then we look in here and we're going to try and do a summation. This is the part that I don't think I actually want to do this way, right? So if we instead looked at how this was working with each individual element, right? So, you know, and you could think of it more this way as well. So if we were looking at each individual element here, R, G, and B, like so, then we could probably say, well, all right, now we just need to figure out what the shuffles are, right, that produce the value we need. And let me take a look here, but I think that's really it, right? So I think we can boil this entire thing down to literally just doing that. Oops. And then do it all in one go and be a little bit happier about it, right? And again, I'm not sure how many of these we actually need here. So I think this would just be the original 8, right? Because we're summing over 8 pixels. So this is how many ops we need. So we have basically, you know, 24 multiply accumulates that have to happen in here. And we just need to make the correct shuffles out of the original loads to make that happen, right? And then again, we can unwind this further by, or simplifying it further by, again, doing these loads in a more structured fashion. But for doing one row, this is basically what it looks like. And then we can also probably look at what this is actually doing to see whether there's a way to make this separable as well. So we just do, instead of interior loops, we just can do, you know, row sums and then column sums. I don't know if there's a way that we can potentially do it that way. But hopefully as we work through this, we can, you know, think about that. So anyway, taking a look at this, if we want to look at what the shuffle is that produces the correct values here for just the R's, right? Which is, I guess, what we need to have happen here. That's just going to be the same transpose as this, right? So loading these up, I think it's just the same transpose, actually. Like, I want to say that we can just do that and then call transpose. I think. So maybe I didn't even have to blow that part out. So I think I mean, correct me if I'm wrong here, but I think if we just have 2 of these, right? And then we load in, or I guess I should say like this. Because the transpose is symmetric, right? It transposes, it doesn't care at all whether you started in one orientation and transposed to the other or vice versa. So we should be able to just load these in, transpose them both, do the op, I think, right? Yeah? Oops. And I guess, so, well, okay, so not quite, because we also, in addition, we need the weights to affect everyone. So the transpose puts us so that we have all of our R's, but we still, I guess that's not true, what I said. Because we still need to, we would still need to collapse the sums. So this would not like get our horizontal adds in. So maybe I'll take that back for a second and say maybe we don't do that, because since this is a straight sum, this just needs to replicate a particular value, right? Like it just needs to say, look, we want to take S0R and we want to just have all of that, right? In each case. So since this is RGB, I guess it's this, right? So maybe this is the right way to look at it. You just go by each of these values. Yeah. So I guess, yeah. Man, this is why this kind of stuff is so annoying, right? You can see how long it takes to do code like this. It's just, this is why SIMD is not good, right? And you usually want this stuff to be automated. And unfortunately, we still don't really have particular good ways of doing it. Because it's just like, your brain is having to think about too many like indexes and how things are sliced up. And it just, why, you know? It's just like a bad way of designing the way you're supposed to express things. And I really don't think it has legs, you know? You shouldn't be really doing this yourself. Especially now when you consider the fact that shaders are a good example of how you can just do this stuff. And when you have properly unpacking loads, you just don't have to think about it anymore, because you just write the code like you would have written it for Scalar, and they can run it at speed, right? So anyway, kind of a side rant, but doesn't matter. So anyway, yeah, if we take a look at the loads here, let's get this back to normal. So each of these shuffles should just now work, I think. Because again, they're just expansions. You're basically just replicating a particular value out. And I think that should be it. And this should line up exactly, at least in theory. Oops. And there we go. So I think that loads everything. I'm not sure why this is complaining. Oh, that's supposed to be an F32. I guess. Do we have a load for these somewhere? You would think that we would, but I'm not actually sure we do. Apparently not. I feel like we should have a load for these. Let me go ahead and make one, since I don't see one. Maybe that. And this just literally does exactly what this does. Oops. And maybe that's a little too cheeky. Love that caps lock key. Never want it. Still kicking. Probably should just go hack, put in the registry thing that just disables it. Anyway, so here's the load for our data type here. And I can go ahead and load F32X these. And then the nice part about that is too, now then we can stop with the casting nonsense, which is always kind of annoying. I hate the way Intel designed these intrinsics. They're so bad. Like, you don't want to have to cast. It's just like, here's the address to load from. Why do I have to cast it to a float star? Like, that doesn't really make any sense, but all right. So in here where we're doing the adds, let me just take a look. So this is actually an F32X. So when we do this multiply here, I guess that will just do the F32 times the F32 and we'll be done with it. And that makes sense now I think about it, because it's like you're not going to have different coefficients for R, G, and B. So I'm not sure why I was writing it that way, but all right. So where's our shuffle 4x? So we kind of set that up so that we would pass in the two different things to use. In this case, it's just replicate. I might actually make a custom one of these that's just like, maybe even just a function that's like broadcast, you know? And I don't know, again, like maybe we already had that, but I don't think we did, because we haven't really done much with these. So there's not really a lot in them, you know what I mean? But I'll just double check to see if there's a broadcast. Yeah, I don't see one here. So I'm going to go ahead and make like a broadcast where you just say, all right, here's the value that's coming in, and here's like, well, you know what? Now I think about it, it does have to be a macro though, because if you want to specify which one, you have to be able to specify that at compile time. It's not actually a runtime thing. So I think it would have to be one of these. So broadcast 4x would just say, look, here's the one I actually want. And here's like the element index, you know? And then it would be a shuffle, where we literally just use the same index each time. Actually, you know what? It can just even call the original shuffle. So I can just say shuffle 4x, A, index, index, A, index, index, right? and then it should work just fine. So this can just be changed to a broadcast 4x, and then this can just be done once, which seems saner. And then let me just change all these. Shuffle 4x's to broadcast 4x. All right. And what else? Oh. Not sure how 4 got in there. All right, so let me take a look to see what the compiler generates now. I just want to see what it generates here. If I go through this code, here we go. So here's us doing the loads, and then we're just doing shuff mul, add, shuff mul, add, shuff mul, add. Much nicer, right? So now we're just dumping the shuff muls into the ALUs. They're gonna have a party with that. And then we're going to loop. So it should be pretty hard for the CPU to screw that up. I mean, you're just basically giving it a huge bunch of flops to chew on. So I'm a little bit more comfortable reasoning about what that's going to do or how we can work with it. So that's fine. Let's take a look and see if it's at all sane in terms of performance. I'm going to have to turn the multi-threading back on, obviously, but let's just take a look at that. Of course, we also may have added a bunch of bugs there. That's sort of a separate issue. But what are you going to do? Yeah, it looks like we've got a little bit of bugging in there. Looks like there's a bit of a chromatic aberration, right? So I think we do have a little bit of a problem in there, but not much. Let me just see what that did to it. Okay, so yeah, I mean, you can already see though, like unless I accidentally removed some of the ops, you can see that actually is a reasonable speed improvement. So I do think that the way we had written that before was just a little bit squinky for the compiler probably wouldn't necessarily know what was going on there. So that's not as good. So let's double check. Let me see what I may have screwed up there. Because again, like I didn't think particularly hard about what we were doing here, and I don't really remember if this was going to be an issue there. So if you look at how the broadcast multipliers work here, so we're selecting individual values out of the spec texels, which I think are loaded out of the correct place. And so if we're getting a chromatic aberration there, again, here's that transpose. So that transpose is like re-interleaving these things, right? And that should be fine. So yeah. So let me just double check what we're computing our weights as. So the weights are packed in here as what? So the weights are just packed in here as the TX. The Texel X is the element. Oh. Hang on a second. So I guess that's fine. because that's just doing multiple of these at a time, which is what we would expect. So this is just figuring out multiple, it's producing, it wants to produce 4 of the destination pixel at once, right? So that's unsurprising. And so when it's doing the multiply here, it just wants the broadcast because it's trying to take the source and spam it out to the entire side of it. However, so when I look at this, I'm trying to figure out where the heck is that chromatic aberration then coming from. If we look at what's happening here, yeah, so this is busted. So this is loading, this is going to go by an entire vec3 is the problem. So this actually needs to be more like this. Because that was loading strided poorly. It's supposed to load by 4s, and it was loading by 12s. Right? There we go. So again, we literally just did nothing there. I mean, we didn't even do anything, but we got a speed win from it. And again, that's just because we got rid of some cruft that the compiler couldn't understand, right? So literally all we did was, I mean, we shaved, what did that got significantly faster. I don't remember what the actual number there was, but it used to be 30 and now it's 10% of the time, literally just from rephrasing it, right? Like all we did was rephrase it for the compiler and off we went, right? So that just dumps a ton of junk into the ALUs, lets them chew through it, and that's a reasonable improvement for us. What I don't know is to what extent could we just get rid of some of these SYs, and that I don't know. So it would be relatively free for us to rephrase this thing so that instead of working the way that it works now, instead what it would do is it would just tell us which row to load, and so sometimes it just wouldn't do that. Just wouldn't load a row at all, right? And so I don't know to what extent we can actually do that, and I guess I wouldn't assume that it would be very frequent, but if we kept our cosine fall off a little bit sharper, we could imagine doing something where we took the cosine fall off and we sharpen it so that it's not quite the cosine fall off, or that it drops down, it loses a little bit of energy there or something, and keeps us from having to load certain rows. Again, not sure to what extent we really should do that, because I also don't know. We could maybe switch to just a separable blur here, and that would just be way faster anyway, because then you don't have to do 64 wide. You just do 8 wide summations, right? And that might just be the smarter way to go. So let's think about that for 1 second. If we did want to make this be something where we separated out those sum values, just trying to think of what the cosine actually looks like in that case. And could we? I'm just trying to think of, could we switch to some other thing? I don't know how separable cosine is. But, it doesn't have to be a perfect cosine. So that's why I was thinking, like, a Gaussian blur is separable. And a Gaussian and a cosine are obviously very closely related in that way. So we could theoretically just use, a value that was going to be separable and go from there. So if we look at, like, cosine curve and like... Is that right? Wait, what's the right way to produce the Gaussian curve? I haven't done this in so long. Hold on a second. Gaussian normal distribution is where's... Give me the equation, please. Because it's you know, it's what I wrote, but you got to have the right parameters to make it look useful. So it's just the negative. Well, I guess we don't have to care about specifically how we put it in there, but it's just that one there. But and then we got to shift it over by something, right? Because we need it to come off of there. It probably isn't a particularly great approximation for the cosine either way, but x minus b squared 2 over 2c squared. No. I'm so bad at Desmos. Yeah. All right. Desmos is so good, isn't it? I feel like we need more parameters than that. A to the e negative x minus b squared 2c squared. Oh, did I put the squared in the wrong place, though? Let's try that one more time. There we go. Much better. And then I guess we also want the a here. Can I get these sliders to be a little bit more... These need to be a little bit more granular and currently aren't, but... Desmos is just so much fun. I mean, look at how nice this is. They deserve some kind of award for something. Right? Wouldn't you say? So, you know, it's not great, but it's not horrible. So if you take a look at how that's summing up the values there, right? A Gaussian is something that we can just multiply on various axes and it would produce the correct result. And so we wouldn't have to, you know, it would be a shaping curve for this. We could also just multiply this on both axes. We could just use the cosine curve and multiply that on both axes and just say, hey, that's what the answer is going to be. So this is apparently, you know, just randomly Googling for it. This seems totally like something people are okay with doing separable. So, I mean, I assume, I don't actually know. This is just doing it in one frequency domain. So, but if we were to just use this, I know we can do this one separable, and I assume the cosine one, if we multiplied it, would still be okay. It's basically a cosine squared fall off at that point, I guess you could say. I'm not sure how you would really look at that, but if you imagine the difference between these two things, like, you know, would we really care which one of those we were using? You know, probably not for lighting, especially because it's just kind of made up anyway. Like, there aren't really surfaces that are going to be reflecting things in a perfect Lambertian distribution anyway. So it's not like there's something particularly physically accurate about doing that as opposed to doing that, or vice versa, right? So if that's the actual cosine curve and we compute this as the actual function for it, it seems like that would be fine. You know what I mean? Like, that doesn't seem like a particularly bad approximation. So that's another thing that we could do here. Instead of actually looping over both of these, we could do something where we produce a summed row value and then we produce summed column values out of those summed row values. You know what I'm saying? And it seems like that would maybe be the smarter way to go. So like we take each position and we do the cosine fall off curve if you were just doing it by a row. And then we do the cosine curve if you were just doing it by a column. And we call that our answer, right? And we could leave both of these in place and take a look if we actually see a particularly noticeable difference between the results in here. And one thing I can do is I can, again, because we haven't worked on the quality yet, I can turn the like transmission rate of this thing down. To darken these as well, if we want to do that. And that would allow us to kind of see what they look like a little bit better, just because we're not trying to do any exposure curves here. So it's kind of hard for us to see what our like octagonal maps look like if they get even, you know, to the brightness that we would probably want them to be. Actually, we still wouldn't really be able to see them very well. So keeping it in here would allow us to switch between those two pretty easily there, right? So again, just taking a look at what we're producing for these maps as we go. If we now switch to separable, what we could do is see if there really is much of a difference between the two that we would care about for transmission. And I don't really know that there would be, right? Again, these maps on the side here are the actual light transfer maps. And so this is, or rather what we actually computed for the lighting and coming in various directions. So these are just the blurs on those that we use for diffuse lighting, which obviously has to account for more angles, right? So if we want to go ahead and change that up, if I go back into this code and say, what would we actually do here to make that happen? Well, in order to do that, we would do two of our loops. We would basically do the loops twice. So we would go down once doing the rows, and then we would go down one more time doing the columns, right? Yeah. So let's go ahead and put an if 0 around this here. And let's see if we can throw in a separable version of it on the way out. So one of the things that's a little annoying about this, just looking at the values that are coming in here, I think I just kind of want to sketch out the routine first. So basically this is this kernel, like basically this stuff right here, where we load a spectexel from somewhere, and then we do the blend on it. I think we're still going to want to do this, right? So we're going to want to load the SY tiles and go down the rows, and we're going to want to do this operation the same way we're doing it here, where we are summing up 4 of these at a time, and then we write them out, right? So I think this structure actually still remains this right here. So this would produce the first pass where we, produce output values that are sums of rows, right? And The difference is we'd actually write out, so rather than summing this here, we would actually be summing it like here, right? And this sy we would also use to determine where we were writing it out, you know? Now, we probably don't really actually need to do the transpose there, because when we load it, because we're going to do another op on this, right? So we could probably leave it in the form that it is and then only do the transpose once at the end, but we can talk about that in a second. So this would basically run through the entire thing once, right? And in fact, we could change that sy and just look at it as like a ty as well, right? So if here I basically said like, yeah, we're going to use ty and tx here. We're going to delete the sy version of this thing. And so in here, it would just literally be that, right? So we go through, we load the weights out. We would do the summation here. We would output the value, and that would run through the array one time. And then we would also want our second pass to be exactly the same, only now when we do it, we're going to be doing by columns, right? So where we load values out of where we load values, they're going to be from the diffuse texels, not the spec texels, right? They're like intermediate texels. And so we would get these out of the... You know, something would happen here, right? We would then load rows of the int texel out, so we would be loading like 4 wide. Trying to think of how you would even do this exactly. The problem with it is you actually... The problem is actually in the intermediate storage. So you actually would want to just be leaving things as R's. So I guess you would just load 4 wide and do 4 columns at once. And then you would swizzle the 4 columns to write them out, I think. Yeah. So I think then what you would do here is you'd say, all right, we're then going to load 4 columns at once, and we know there's 8 columns. So, yeah, you would load those. You would sum across the column and output the value. Right? I'm not going to have time to finish this today. This will have to be tomorrow. So yeah, so in order to load the correct columns, here we would probably still just do the loads manually. And again, we're going to have to pretty much bake these values. Like the loop's going to have to be written, customized, I think, to a particular size. I don't think we can leave it flexible, but I mean, it's kind of already not flexible here, right? Like this already assumes a certain number of these. Anyway, so if we go in here and say, all right, for these, we'd have to load all 8 columns in, that looks more like this. We'd have to do all of the ops on them, and the problem that you would then get is you can't actually write them out because they're in the wrong format. So, yeah, it's just really ugly. You would have to do the ops here. So maybe you would transpose here. Let me think about this. So I suppose another way to look at this would be that if you were going to just replicate the weights themselves, I'm trying to think if what I'm saying is true. If you were just going to replicate the weights themselves, could we maybe just leave this in RGB the entire time? I think we probably could. So, bear with me for a minute. So suppose in here, as we load across this row, we don't actually do any broadcasting, right? So what this is doing here is it's saying, well, I need to produce the R value for this thing, right? And so rather than thinking of it as as a RGB, whatever, what if we said instead of that, that's not what we were going to do. So instead we just said look, this is RGB, this is just element 0, right? Just trying to sketch out what this might look like. So suppose we were just going to start computing element 0 and we said, look, these weights are going to be set up so that they multiply this thing properly. And we have this broadcast. And instead of doing the broadcast, we're just going to say, look, S0, we know that we could figure out what the values are that want to multiply it in to produce E0, right? So we could just say instead, no, it's just that, right? So we're just doing the multiply between these two. And then what we want to do is just sum those up. So we're just going to do that. So we just have weights for each of the things that we actually want to load out. I guess trying to think exactly what this does here. So and it wouldn't be, because the weights now are also not based on the weights now would not be based on anything in particular. Because if we're just doing row and then column weights, we have far fewer weights. There aren't 64 weights anymore, right? So what we could do is say, look, we're just going to record the weights that we would actually use for the multiply. We'll do the multiply, and for each output element that we have for the row, of which we know, well, and in fact, we can just write it immediately at that point, right? It's just a store. So we can just say, yeah, we're going to write this thing out. Somewhere, right? And off we go. And we would just do this for each of the 6 elements. So that's one way we could do it. So we just record what each of these weights is supposed to be in some kind of a weight distribution thing, right? Furthermore, actually, thinking about this a little bit more, it doesn't really even need to be something it's not structured anymore, because it's literally just one set of weights. And you would apply it in both cases, I think. Maybe that's not true. They're the same set of weights in both cases, but they might be formatted slightly differently. So if we actually just loaded things in, multiplied by the weights, and accumulated, and that was actually the value that we stored in there, that would give us, so it'd be 36, max or whatever per row. So it'd be 288 of those, and then another 288 of those in the other direction. Right? So it'd be like half the number. And that seems like not as much as it should be. Although that probably was multiplied by 3, wasn't it? I don't know if we were looking at that correctly before, but... In fact, what is the actual number here? So now, because we can see it pretty easily now. So if we take a look at how many are in here, we've got 8 times 2 times 8, and on the interior there's like, what? 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 3. So there's 24 max. 8 times 2 times 8 times 24. Yeah, so it was multiplied by 3. We forgot the 3 in there. So, yeah, if you take a look at the ratio, it would be about 5 times faster in theory if we did it this way, unless there's some other like intervening factor, right? So you would come through here, you would load up a row, you would compute what the smoosh of that row is in RGB directly. You wouldn't like unswizzle it, I don't think. Assuming that I can actually do that properly, which I don't know if I can. I think, yeah, I don't know if we can actually do this, because if you think about what has to happen here, so in order to get the correct value in the first slot, weights times SO0, it doesn't actually have a way to get that other R in there. Right, like these don't allow you to do the cross terms properly. So I don't think we can actually do it this way, unfortunately. So I'm not sure. I'm gonna save this for tomorrow. I'll get rid of this for now. We'll have to think about how to do it exactly. Because it's really just a question of how do we get it's just how do we get stuff in the right spot. So for now, we'll just say, look, we know we can get that. We know we got a good savings out of it just by making it a little bit clearer to the compiler how to do it. And so now it's just a question of can we improve it further from there. But otherwise, it seems okay. We'll go to a quick Q&A. Are there any caching concerns? So I don't know that there are any caching concerns with the voxel. So, yeah. So what did we say? It's that. So I don't know that there's any caching concerns with the voxel at the moment because it's so large that we will not be getting good cache out of it really in terms of anything other than just regular streaming performance, right? Now, that can be improved by switching away from float. We would start to get down to areas where we might actually be able to do something good there. And furthermore, if we wanted to, we could get like really down into reasonable range by also, again, reducing the number of stacked voxels we've got. We could also do some things like play with the resolution in terms of Y as well. So there's a lot of things we could do to shrink the amount of data that we're working with. The biggest one would be not using floats anymore, and we could definitely experiment with that. But at the moment, yeah, we're fully blown out right now, and so we are not going to be in a particularly great cache land at the moment. Now, that said, separate from that, I think we have done a good job with caching concerns in terms of the order in which we're working on things. So what you'll notice is we very specifically, and I did this 100% intentionally, right? Each tile is updated by itself. So on a particular thread, it loads, operates, and writes completely one tile at a time. And the reason for that is that way, although we do have no real good control over the sampling of the diffuse map, which we randomly have to pull from because we have no idea, like as the rays go out, we have no idea which ones are going to hit. In terms of the operating on and writing out of the diffuse map, that is done completely contained. And so when we want to turn the ratchet on that, we're in very good shape to do so. And we're already probably getting very good caching there because we don't do anything funky. Right? So that was intentional, and that's to keep us from writing scattered. If we wrote scattered, we would be in big trouble, but we don't do that. I don't know that there's anything simple you can do to reduce the amount of flicker if you want it to be very stable and still be fast when you update. You certainly can, but you're just in the realm of denoising. So at that point, you have to have, you got to start looking at filtering, right? Like how you're going to filter the results. I think probably if you were an expert at filtering, it probably wouldn't take you very long to clean up these results because there's not very much flicker. So basically what you're looking at there is just you've got to filter. And that is something that you probably want to be more of an expert on than I am to know how long it would take you to reasonably build a good denoising system for this kind of a thing, right? The light seems to be repeating outside of the light box. Is it still there? And if so, is it a modulus issue? No, so that's just because of the Texel lookups. So right now, we wrap the Texel wraps, right? So when it does lighting, it's just going to light outside it. We don't care about that because you can never see outside there, right? The only reason we're ever seeing that stuff right now is because we aren't actually properly centering our... So like, if you look at what's happening here, and you pull out, right? You see that voxel? Right now, we're letting some garbage happen. Like this should just be sliding as we move. So the place that you're looking at the camera should always be in the center. And right now, since we're not doing that, you can still get times when you will see across the edge of it. We never want to allow that to happen. So we have to fix that slide anyway, and that's just a question of writing the code that properly aligns it with where you're looking. And that's all we have to do. So I don't care that the lighting repeats out here because you can never see it. You will never see that on the screen. So I should be fine with that. You mentioned something about shaders. being better at this kind of job. I lost your point on that because of me being unfamiliar with the environment. Can you please explain this a little bit more? Yeah, so one of the things that you'll notice is like when we wrote our shader code, okay, you'll notice that we never had to think about SIMD at all. Ever. Right? We literally never, ever, ever wrote anything in here that had anything to do with SIMD. We just wrote, this just looks like regular code that operates on like one value, right? And yet, when we write CPU code that does basically the same thing, we have to do all of this mental work ourselves, you know? And the question is, why is that? And the answer is very simple. The GPU already has in it the proper memory crossbarring on loads to turn things that are packed RGB, RGB, RGB into Rs, Gs, and Bs. And then when it's done, it has the bar to write them back out that way. So rather than us having to do all of our code that way, GPUs were just like, hey, you know, everyone needs to store things compactly as little units that should be packed XYZ, XYZ, RGB, RGB. Let's just make a thing that will unpack those into Rs, Gs, and Bs while we're computing them, and then put them back when we're done. Intel just never did it. They just simply didn't do it, and I don't know why they didn't do it. It must have been too hard for them to do in the store buffers or something, or the load buffers, I don't know. But they just never did it. And so it's all this huge headache when you want to do something and you decide to do it on the CPU side. It's this huge headache. It really sucks. And with AVX512, because that was designed originally as a shader API. So AVX512 was originally LurbNI, which was originally for GPU, right? That has proper, it's called scatter gather is what that's called. It has proper scatter gather so that actually finally you can just load and do your swizzle on the load and it's free, right? Do your work and then write it out scattered. So it's the same is true of Neon. I don't know if you've ever seen that. But the ARM SSE has that in it. So basically the problem is just that on the CPU side, there is no way to actually do it clean. You can't load packed data and get it out into properly aligned form without a crap ton of shuffles, as you've seen, right? And so it's just a limitation of the hardware. If at some point AVX512 became a standard feature set, which at this point may like literally never happen. I mean, I don't even know if Intel's going to be shipping the chips that anyone cares about anymore. Like, I mean, AMD is by far the performance leader now. Like, I mean, they are just crushing Intel and will continue to do so. Like, Intel can't even manage to fab new chips anymore, it would seem. So, like, I don't even know if we'll get AVX512. It may never happen, right? It may be that, like, you know, sort of a marginal set of Intel chips supports AVX512. AMD never adopts it, and AMD is dominant. In the x64 space, Neon, of course, is its own thing, and ARM, you know, may become more dominant as well. It already is pretty dominant in a lot of ways. And so, you know, it may be that we never get AVX512. I don't know. Yeah, and just to be clear, like, so features like JAI's SOA AOS stuff, while obviously a good thing and you want your language to make it easy for you to write things that reorganize your data without you having to rewrite your code, One of the problems with it, again, is that there's nothing JAI can really do to solve this particular problem, right? Because the problem is we need this data in the same format as the GPU needs this data, right? And so it ties that, like, there's nothing, JAI can't reorganize that because it has to be in that format. And so there's really nothing you can particularly do there, right? Now, there are things that languages can do to make it easier for you to write messed up code like this, which is they can provide tools for you to ask it to do, like, arrangement of your code for you in structured ways. Someone just mentioned ISPC, and yes, that's a very good example of language additions and then a compiler that backs up those language additions to allow you to more easily write scalar code that can be turned into SIMD code without you have to do anything, and it will still be good SIMD code, right? So that's a great feature. But again, not really present in much, in our tools very much yet, right? Oh, someone says the Intel intrinsic guide is broken? What's broken about it? Looks fine to me. Yeah. Maybe you've got a route problem? I don't know. It's loading for me. Yeah. I just did a Control-Shift-R. So that should load it outside of the cache, right? That's a forced reload. Oh, you can't specify architecture. So you're saying you can't, like, click? Yeah, it does look, as soon as I clicked on that, it broke. So it does look like they broke it. Yep, that is true. It would seem. They broke it. You can use the UOPS page for this, though. So that's another option, and that will probably work, right? So, you know what I'm saying? This won't tell you what the intrinsic is, so I don't know. At least I don't think it will. Not sure. Maybe it will. I don't think it will, though. But for doing stuff like finding out what the instruction, like, performance is, this is actually better anyway. So, like, I would encourage you also to use this as much as possible. And unfortunately, it doesn't have intrinsics in here. It'd be cool if they added that, because then there'd be no reason to use the Intel intrinsic guide. You just always use this. But all right, I'm gonna wrap it up. I'm really liking this lighting. I think it's going to be a lot of fun to kind of tune it up a little bit. I think because it's just so nice to be able to walk around and have that kind of realistic, like, play off the walls and everything. And I don't know. This is getting really cool. Anyway, all right, let's close it on up. Where's my web browser? I closed it. That's not what I meant to do. All right, thank you everybody for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series at home, you can always pre-order the game at handmadehero.org, and it comes with a source code which you can use to follow along at home. If you want to try writing a separable version of that filter yourself, that would be a great thing to do tonight. Because it's a pretty bite-sized problem, And you can go look up separable filters and read about them before I get into that, which I don't know if we really need to do, but I do think we want to at least try it because it should be significantly less ops, and we do need to reduce the number of ops in that code. So something to think about. All right, I'll be back here tomorrow to give that a swing. Till then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.